So today we're going to finish off the lecture on inclusion exclusion, and we're going to do the subset of chapter 6 that I think we have time to cover on advanced combinatorics. You can easily teach an entire semester on advanced combinatorics. I want to try to highlight a few of the key features that will be useful later. So first, let's go back to inclusion exclusion. So this is an extremely powerful method to calculate probabilities. So let's just do one more example. So we're going to calculate the probability of a derangement. So reorder 1, 2, ... n so that new sequence has nothing in same place as the original. So what this basically means is that when you reorder the numbers 1 through n, everything moves. So if I give you 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, is this a derangement, yes or no? No. But if I give you 1, 2, 3, 4, 5, and 2, 3, 4, 5, 1, is that a derangement? Yes. Unlike me, if you've taken abstract algebra, you might have seen something like this with permutations. And so trying to count maybe how many permutations do you have where everything is shuffled? That could be a very interesting question. All right, so what we want to do is we want to calculate how many derangements are there. Okay, so given that this is right underneath the phrase inclusion exclusion, it should be pretty clear what method we're going to use today to calculate this. What we want to do is we want to calculate events that are simple. Okay, so in inclusion exclusion, you always have to choose what are the basic events that are easy to compute, and then once you have those, then you calculate intersections. So the idea, intersections are easy, unions are hard. Choose events we can, I'm sorry? No. Nope. Unions are hard. Like when we did the bridge problem, it was hard to calculate that at least one person has all cards in the suit. But the probability that you and I both have cards that are, hands that are one suited, that was easy. So the intersections are easy. Choose events we can easily compute. So we need to figure out what should the building blocks be for this problem. And so for this problem, I will have to just keep walking here. It doesn't seem to like this classroom. So for this problem here, we want to choose easy events to calculate. What would be a good event to calculate? We're looking at derangements. Good, so that 1 is in the same place. When you say 1, do you mean the number 1 or one specific object?
Either way.
Which way?
One specific object.
One specific object. So we'll have the events k is in the right spot. These will be very easy events to calculate. So Aij is I and j in the right spot, i.e. they don't move. If we calculate the probability of A1 union A2 union AN, what is this the probability of? At least one is in the right spot. Is this the probability we want? No, this is not the probability we want. How do we get the probability we want from this? It's the complement. So rather than calculating the probability that everything moves, let's calculate the probability that at least one object doesn't move. And if we know the probability that at least one object doesn't move, then we can calculate the probability that everything moves by looking at 1 minus the probability at least one moves. So what we want is 1 minus the probability of the union I goes from 1 to n of AI. And if we can compute this, we'll be in great shape. OK. So let's try to calculate the probability. I claim the probability of A1 and the probability of AN. Does it really matter which one object we talk about being in the same spot? No, they're all the same. What's the probability that the first object is in the correct spot? Any thoughts? Yes?
N minus 1 factorial over n factorial.
Good. I'll write it even more pedantically as 1 times maybe n minus 1 factorial over n factorial. I have to put the first object in the first spot. And then for the remaining n minus 1 spots, I have n minus 1 objects to order. And then there's n factorial ways to order n objects. So the probability, oh, this becomes really nice. It's just 1 over n. Now we can look at the next level. What's the probability A1, 2? So this means 1 and 2 are in the right spot, all the way through the probability of A, n minus 1 and n are in the right spot. So how many ways are there to have objects 1 and 2 in the correct spot? Excellent. I have to put the first one in the first spot. I have to put the second one in the second spot. And then I have n minus 2 factorial for the number of ways to order the remaining. And I divide by n factorial. And we get 1 over n minus 1. And I'll put some kind of strange arrow to just say the pattern continues. If I had 3 objects, it would become 1 over n minus 1 and minus 2. OK? And so now what we can do is we can now try to calculate what is the probability of A1 union AN. This is going to be the sum, I equals 1 to n, of the probability of AI minus the sum I, let's see, 1 less than equal to I less than j less than equal to n of the probability of Aij plus the sum 1 less than equal to I less than j less than k less than equal to n of probability Aijk, et cetera, et cetera, et cetera. So we just keep going down like that. All right. So now, what's the probability of the first one? So what's the probability of AI? What do we get for the probability of AI? 1 over n. How many choices do we have for the first one? We have n. OK? So we have n choices for the first one. So this is going to be n times 1 over n. For the second one, how many choices do we have for the second one? N choose 2. 1 over n minus 1. The next one would be plus n choose 3, 1 over n minus 1, n minus 2. And so on, and so on, and so on. So now the question becomes, how do we simplify the algebra? So if we look at what's going on here, n times 1 over n, that's not so bad, that's 1. We have n minus 1 over 2 factorial times n minus 1. What does that equal? So the next one just becomes minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial. And it's either plus or minus 1 over n factorial at the end. Has anybody seen a number that looks a lot like this? Where have you seen something that looks like this? E. So by doing a little bit of algebra, we can actually get a nice answer here. So our answer is the sum, k goes from 1 to n. And now let's write things a little bit carefully. So we start off with, we have a 1 over k factorial, and we have a negative 1 to the k plus 1. Because we start off with a probability, we start off with 1, correct? We start off with a positive term. And this is equal to the probability of the union, I goes from 1 to n of ai. And this is 1 minus the probability we want, right? This is 1 minus the probability of a derangement. So we could do some algebra, and we get the probability of a derangement is 1 minus the sum, k goes from 1 to n, of negative 1 to the k plus 1 over k factorial. So summation notation is extremely powerful. It's concise. It allows us to write this answer very cleanly. The negative 1 changes all the negative 1s by 1. So I can just drop this plus 1 over here. I can pull that out. And so this is the same as 1 plus the sum, k goes from 1 to n, of negative 1 to the k over k factorial. That's actually very nice. We no longer have this shift in index. Is there any way we could bring this 1 into the sum? Yeah, if you take k equals 0, we've decided that 0 factorial is 1. This is the same as the sum, k goes from 0 to n, of negative 1 to the k over k factorial. And if you take the limit as n goes to infinity, this goes to the sum, k goes from 0 to infinity, of negative 1 to the k over k factorial. This is just e to the negative 1. So if you see in the series expansion for e, this is using e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And this is just taking x equals negative 1. So there's a really nice probability that you get a derangement. It's about 37%. So there's a lot of good stuff going on in this problem. It's a nice example of inclusion-exclusion. It's a nice way to review summation notation. It's a nice way to look at limits. This is a very rapidly converging series. It's alternating, and the denominators are growing very fast. So this is going to converge very quickly to 1 over e. The probability is also quite high. You have a probability of 1 over e that at least one number occurs in the same place as before. Well, if you think about it, you've got n numbers that are being moved around. What's the probability that nothing comes back to where it starts? Does it seem likely that it should happen at least once? How many times do you think it should happen? Would you be surprised if it only happened once? Do you expect it to happen 2 times, 3 times, 4 times? This is something we'll study later in the semester, trying to understand how often would something like this happen. But as an aside, how would you try to figure out how likely it is for this to happen 2 times, 3 times, 4 times? What would you do? Yes? Code it, right? When in doubt, write code. Investigate. Look and see how often does it happen at least twice, at least 3 times, at least 4 times. Run the code. Try to see what those probabilities are. See if those are nice numbers. This is a really nice probability that it happens at least once. What's the probability that it happens exactly once? Is that a nice number as well? Or is it just the sum of the probabilities of it happening is nice? Okay. So there's more we could do on inclusion-exclusion, but I think this does enough to give us a sense of what these problems are like. What I want to do now is I want to do circular orderings. And I'm going to do a lot of these topics fairly quickly just to have these on your radar screen. So imagine you have people sitting down in a line, or people sitting in a circle. Is there a difference between these settings? Yes. Unless I put in labels on these seats, if I'm playing bridge, north, east, south, west. If I put labels on the seat, then it's the same as the labeled ordering over here. But for a lot of things, I only care about the relative ordering at the table. I only care who's on my left, who's on my right, who's across from me. I don't care which of the 4 seats. If this is the Old West and you're in a canteen, that might be different. You might not want the seat where the back is to the door. Okay? We will assume we're not in a situation like that, and that you don't have any mortal enemies who will shoot you while you're playing poker using the results you've learned in this class. We will assume all that matters is the relative ordering of the people. In this place, if I have 4 people, how many ways can I put the 4 people around? Bless you. 4 factorial. I have 4, 3, 2, 1. So on a straight line, there's 4 factorial ways to put 4 people down. What about on a table where we only care about relative ordering? How many ways are there to do it when I only care about relative ordering? 3 factorial. Why 3 factorial?
Because you can just rotate.
Good. You can always rotate and assume whomever you want is in the top seat. So you can make one seat special and just rotate everybody to be in that position. Because I've got to put myself somewhere. I might as well put myself on the top. Or maybe that sounds too arrogant. I'll put myself on the bottom. Right? So you always have a choice of where you want to start counting from. So if you choose a special person, you can just start counting from there. So I've got one choice. And now, how many people do I have for this spot? 3, then 2, and then 1. So it's n factorial on a line versus n minus 1 factorial on a circle. Not a huge difference between linear orderings and circular orderings. This is a common trick. It's putting in a label and then removing the label. So we add and remove a label, essentially. The reason I want to do this is twofold. 1, this is just good combinatorics to be aware of, and 2, it leads into the next quantity we're going to look at, which is the multinomial distribution. What do you think the multinomial distribution generalizes? The binomial distribution. Okay? So what we're going to do is just move it like this because technology has failed us. Okay. What is the most interesting state to try to spell? Mississippi. That's the one we always use, right? How many of you know the joke, Mississippi is a hard state to spell? Spell it. Very good. Why is this such an interesting state? Only 4 letters, but look at how many letters are written. So there's only 4 distinct letters. We have 1 M. We have 4 I's. We have 4 S's. We have 2 P's. Right? So one of the things you can do is, how many words can you make from Mississippi? Do you consider the word miss different from the word miss?
No.
They should be considered the same word. I don't care which S I use. I could use these 2 S's. I could use those 2 S's. I could use this I. I could use that I. There's lots of different things. So if I want to try to calculate, this is a very tough state to use. I'm traveling to Maine today with my kids for 6 hours in a car. All right? Wish us luck. If we want to calculate how many words can we form from Maine, is that easy? Why is Maine so much better than Mississippi? I'm not talking football for the college football fans here. They're all distinct. So there's 5 factorial words. And we could even say distinct words. Mississippi is much harder.
Okay, but you don't mean, so we're counting words as using every letter?
Every letter.
Okay.
We don't want to leave anything on the board. So all the letters are being used. there is a way to get from a case like this to a case like this. What we're going to do is we're going to add extra labels. So what we're going to do is we're going to respell Mississippi with new letters. We're going to spell it M sub 1, I sub 1, S sub 1, S sub 2, I sub 2, S sub 3, S sub 4, I sub 3, P sub 1, P sub 2, I sub 4. So we've now spelled Mississippi using new letters. How many words can we spell of 11 letters? 11 factorial. And now if you think about what's going on, 1, 2, 11. We have 11 spots, and we're putting in all the letters into different spots. Can we distinguish the first I from the second I right now? Yes. Should we be able to? No. We want to remove the labels. So 4 of these spots are chosen to be I's. How many ways can we order the I's among those 4 spots? 4 factorial. We should remove that difference. And so we divide by 4 factorial because we cannot tell the difference between those once we remove the labels. So what we've done is we've added the label, and now we're going to remove it. What about the S's? How many ways are there to place the S's among the 4 S boxes? Once we've chosen which boxes are going to be the S's, how many ways can we place the S's? 4 factorial. So we have to remove that. All right, what's the only thing that's left now? Nope, that's a trick question. It's not just the P's. M. The M is easy to handle, but the M is still there. Let's just pretend that only P was left. We've now got 2 boxes that were chosen to be the P box. So how many ways are there to remove the label on the P's? 2. Or better, 2 factorial. As you've probably learned by now, I love writing things that in some sense I don't need to. I love writing extra factors of 1. The reason is it makes the formulas a lot easier to follow. Do I need to remove the the labeling on the M? No, the key word is the. There is just one M. Why would I want to remove it? Yes?
It's nice to check that the numbers on the bottom add.
Yeah, the numbers on the bottom will then add to the numbers on the top. And if I remove the 1 factorial, then the sum of the things on the bottom is everything on the top. When you have something like this, you should always look at special cases. So a special case would be a state where you only use 2 letters. So consider the state. Okay. This state is very useful in the land of polynomials. How many ways are there to order? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 letters. How many x's? 1, 2, 3, 4, 5 x's. How many y's? 3 y's. What does that look like? A choose 3 or A choose 5. If you think about what's going on, we have 8 objects. We have to choose either 3 spots to be the y's, or we have to choose 5 spots to be the x's. Once you choose the spots that are the x's, then the spots that are the y's are forced upon you. We can write this with the multinomial coefficient as 11, 4, 4, 2, 1. What's a little bit dangerous about writing it like this? Just notationally, what could be dangerous? Yeah, it could be 11 choose 4,421. I probably don't want to know how many ways are there to choose 4,421 objects from 11. If you want to be extra safe, you could put in some commas to just remind yourself that you're choosing 4 objects. The stuff down below has to sum up to the stuff above, so that should control how things go. So these are the multinomial coefficients. Should there be relations between the binomial coefficients and the multinomial coefficients? Yes. What you can do is, I have 11 choose 4. That's the number of ways to choose where the i's go. I now have 7 objects left. So I could say maybe I have 11 choose 4, then 7 choose 4. I'm now choosing, first I chose the i's. Now I'm choosing the s's. Now I have 3 objects left and I choose the p's. I have 1 object left, I choose the m. Should these numbers be the same? Should this equal that? Yeah. So as a nice exercise, prove these 2 are the same. What do you think you're going to have to multiply by to prove that these are the same? 1. In fact, it's going to hint at what to multiply by. 11 choose 4 is 11 factorial over 4 factorial, 7 factorial. 7 factorial divided by 4 factorial, 3 factorial. You see the extra 7 factorial. So you put a 7 factorial up here, you put a 7 factorial down here, you can see the 11 choose 4 coming out. So I'll let you play with that as a nice exercise to just see the different relationships between stuff like this. You can write it down directly as a multinomial coefficient. You can do it as an iterated sequence of binomial coefficients. You just keep making choices one at a time. First I choose where the i's go, then I choose where the p's go. This also suggests a following theorem. Any idea what theorem this suggests must be true? So I've got 11 choose 4, 7 choose times 7 choose 3, times 3 choose 2, times 1 choose 1. What else could I have written?
11 choose 7.
Not 11 choose 7. So I chose the i's first, then the s's, then the p's, then the m.
Oh, you could,
Yes.
you could do like 11 choose 2, 7.
I could have chosen the p's first, and then the m's, and then the i's, and then the s's. So what this is telling you is there's got to be some kind of theorem that if you have a product of binomial coefficients, and you've got some relation on the sums of the bottom and the top going down, it doesn't matter which order you do things. So if you always want, a good way to always think about this is I'm choosing something and I'm excluding the remainder. Then I look at what's left over and then I do the choice. I can always change in my mind the order in which I've done these operations. Okay. Any questions on these multinomials? We're not going to do too much with the multinomial distribution, but you should be at least aware of it. And in some sense, it's just a consequence of multiple binomials. Okay. So we are now at one of my favorite parts of the course, the cookie problem. I apologize, I forgot Cookie Monster in my office. I will try to remember to bring him on Monday. I'm in a rush today to get to Maine, and I don't want to be rushing on the highway. All right. This is probably my favorite combinatorics problem. I have a math riddles page. This was the very first problem I was asked when I was in grad school that led to creating this math riddles page. How many of you are thinking of grad school? Okay, I need to talk to you as to what grad school is like. I was a social chair and a house advisor. I was in charge of happy hour. Not happy hours, happy hour. There was 1 hour each week when graduate students were happy. At Princeton, it was from 6:30 to 7:30 on Fridays. We had ice cream, we had alcohol. Sometimes we had ice cream in the alcohol, alcohol in the ice cream. We'd play bridge, and then we would go back to being miserable. To let you know what grad student life is like, there was the day our dining hall was not open on Saturdays for lunch, so we went to the first closest undergraduate dining hall. Nobody was there. We went to the next closest undergraduate dining hall. No one was there. We then basically found an undergraduate walking around saying, "What's going on?" And they said, "Oh, there's a big party on the street. All the dining halls are closed." So we went to the street party. I don't mind if this is recorded and this gets out. I'm still mad about this. And I saw the head of dining. And I went up to him and said, "Hey, oh, the grad students. Yes, the grad students. You forgot to tell the grad students you were closing the dining halls. Can you please just leave one dining hall open? We don't want to be social. We don't want to go to this event. We want to go back to our miserable existence in our offices on a Saturday and work." And I still remember his response. They've tried in the past having one dining hall open. Everybody just goes to that one open dining hall and nobody goes to the party. The last thing I will say is, for those of you who are considering grad school, at Brown they had a free food email list where they would send emails to the graduate community saying there will be a talk at 4 o'clock in the following room followed by. And the graduates would say, "I can listen to that for pizza," or "Wait, they're just giving cookies or they're just giving crackers? No, it's not worth it for that." So I will say, imagine you have 5 hungry, although hungry I don't really need to say, grad students. This will be your life. And you have 10 identical cookies. Now, nobody here is considering engineering graduate school? Or one person? In engineering grad school, it may not be a reasonable assumption to assume the graduate students are distinguishable, and the professor actually knows the difference between them. In some of the biological sciences, this could also sadly be true. I did have a friend in grad school where the professor, she was in, I'll say either biology or psychology, not to specify too much, where the professor actually did not know her name and introduced her with the wrong name at conferences. I will assume we will have distinguishable graduate students, that you can actually tell the graduate students apart. Okay? I have 10 cookies, 5 grad students. What do you think I want to solve? So, how many ways to divide cookies? So I'm going to assume it doesn't matter which cookies you get. It only matters how many cookies you get. This is actually going to be related to a probability problem that somebody came to me recently. It was on a series of interview questions for people looking at, I think, consulting jobs. So the mathematics behind this is something you might see on some very difficult questions. Can somebody give me a painful way to solve this problem? I'm sorry? So how would I go through all the possibilities? The grad students will have the lovely names A, B, C, D, and E.
Well, one grad student could get all the cookies.
So 10, 0, 0, 0, 0, 0, 10, 0, 0, 0, dot, 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 10, 0, 0, 0, 0. And now what? 9, 1, 0, 0, 0. And we can keep going like that. And depending on how much time we have in the day, we'll talk about how painful this would be. There is a way to do this in one line. Okay? So how could we do this in one line? A lot of probability and combinatorics comes down to, can you find the right way to look at it? Can you find the right perspective? Instead of solving the given problem, is there a related problem that's easier to solve? And so we're trying to divide 10 cookies among 5 people. There's an easier problem. Let's consider 14 cookies. And we will see why we want to consider 14 cookies in a moment. There's something very nice about the number 14 as to where it's coming from. All right. So if I have 14 cookies, let's draw them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I do apologize that I left Cookie Monster in my office. There wasn't time because there were computer issues, as always. Can somebody describe the original classic Cookie Monster to me? Me want cookies. Good description. This is not the politically correct bastardization that Sesame Street has done, where cookies are a sometimes food and he'll sing songs about vegetables. This is the original Cookie Monster. Yeah, absolutely. What will Cookie Monster do if he sees 14 cookies? So he will unfortunately try to eat them all. And so you need to kind of restrain Cookie Monster. Let's assume we can control Cookie Monster enough so that he will only eat 4 cookies and then he'll be stopped. I will post the clip where the Cookie Monster eats the count. It's the irresistible force versus the immovable object. The count wants to count the cookies. The Cookie Monster wants to eat the cookies. They have to work through their differences. Imagine Cookie Monster eats 4 cookies. 1, 2, 3, and stops. Or is converted to the Veggie Monster, whichever way you want to do it. Cookie Monster eats 4 cookies and stops. How many cookies are left? How many cookies are we trying to divide? If you look at what's going on, we've put in 4 partition marks. 4 partition marks partitions this into how many sets? 2, 1, 0, 3, 4. What do those numbers add up to? This is how many cookies A gets. B, C's in the humanities, doesn't deserve cookies. D, and the nice science student who's extremely well funded gets 4 cookies. This is how grad school is like. Okay, I do apologize for those of you who are from the other side of root 2. There's a 1-to-1 correspondence between Cookie Monster eating 4 out of 14 cookies and assigning cookies to the people A, B, C, D, and E. Right? So the solution to our problem is 14 choose 4. And if you actually care, it's 1001. That is the number of ways to assign 10 cookies among 5 people in such a way that all the cookies are distributed. The way to look at this is we have C cookies, and then we add P minus 1 cookies, and we eat P minus 1 cookies. So if you look at it this way, that's the general case where you have C cookies and P people. Okay? So any questions on what we've done so far? Now, I have made fun of humanities students. I've made fun of people on the other side of root 2. I know I have some of you in this class. I have now gotten in trouble. I actually just got a text from Dean Bolton that this was inappropriate behavior. I am going to be hauled in and investigated. So I need to very quickly rectify the situation. What additional condition do I need to put on very quickly? Every student has to get at least 1 cookie. Right? I can't let a travesty like this happen. Right? So I want all students to get at least 1 cookie. Fortunately, all of mathematics seems to be connected. What we're doing is doing a special case of very general advanced mathematics. What I want to do is I want to take the original problem and I want to abstract from it what we're really doing. We're really trying to solve the following equation: x1 plus x2 plus x3 plus x4 plus x5 equals 10. And what constraints do I have? xi greater than or equal to 0, and they're integers. No sharing cookies. No fractional cookies. We're really trying to solve an equation like this. If you go further in mathematics, if you do number theory, if you do partitions, you might say, maybe I want to write 10 as a sum of squares, of 5 squares. Is it possible to do that? There's a lot of questions you can ask along the line like this. You can use generating functions to solve problems like this. We saw generating functions when we looked at the Fibonacci numbers, when we looked at Benet's formula. We will see generating functions again when we get to the central limit theorem. I want to show you how ubiquitous these are throughout mathematics. They constantly keep emerging to solve problems like this. We want to put in some constraints. Some constraints are easier than others. Is there any other constraint you might want to put in? So you may, well, no one will get all the cookies because everybody has to get at least 1 cookie. No one gets 6 cookies. If you want to put in constraints like that, those constraints turn out mathematically to be very difficult. It is difficult to restrict how many cookies someone can get as an upper bound. It's very easy to insist that somebody gets cookies as a lower bound. So we're going to let y sub I equal x sub I minus 1, or x sub I equals y sub I plus 1, depending on which way you want to view it. What am I doing? xi is the number of cookies person I gets. I'm going to let yi be the number of extra cookies they get above the number of cookies they must get in order for this basic notion of fairness to happen. So do I have to do everybody gets 1 cookie? No, I could play favorites. Anybody who's in English gets 1 cookie. Anybody who's in math has to get at least 2 cookies. I can put constraints like that in very easily. And it would just be maybe x1 equals y1 plus 1, x2 equals y2 plus 2. And then that would force the second person to get at least 2 cookies. Lower bounds like that are no problems. So now we get y1 plus y5. What does that have to equal? It's going to be 10 minus 5 or 5. How many ways are there to divide 5 cookies among 5 people? The answer is going to be 5 plus 5 minus 1, choose 5 minus 1. This is just going back to our cookie formula where C equals 5 and P equals 5. So we get that the number of ways of dividing the cookies so that everybody gets at least one cookie is just going to be 9, choose 4. We can handle that problem immediately. We can handle related problems where they don't all have to be given the same number of cookies. This is the power of having good notation. We're really solving this equation, x1 dot 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 plus x5 equals 10. And if we just change things a little bit, it just changes this equation, and then we can interpret this in terms of what we've done before. So I think the question that somebody was given was the following interview question. And they found this online. I don't know which company this is from, so I think I can legally talk about this. So you have 100, we'll say cookies, and you want n chocolate chips. Divide all the chocolate chips among the cookies. All divisions equally likely. Find the smallest n so that at least a 90% chance all cookies have at least one chip. So I will leave this for you to think about. Can anybody give me any facts about n? Yes?
N has to be greater than 100.
N has to be greater than, well, technically greater than or equal to 100, but we can be pretty sure that if n equals 100, it's not going to work. The only way that would work is if we had that one special division where each cookie got exactly one chip, and that would be extremely unlikely. The question is, how much bigger than 100 do you expect this to be? This is essentially the cookie problem. We could go back over here and we can look at what fraction of the divisions will have each person getting at least one cookie. This is the number of divisions where each person gets at least one cookie. The number of total divisions is 14 choose 4. So if we look at their ratio, that will be the number of divisions where everybody gets at least one cookie. So I'll leave this as a nice exercise for you to finish and clean up. What I want to do now is I want to just really drive home how good this problem is and how many other things you can solve. We're not going to have time to go through the painful details here, so I'll erase this. So now assume don't have to give out all cookies. How many ways? So we could have C cookies, C minus 1, C minus 2, 2 cookies, 1 cookie, 0 cookies. We have P people. How many ways are there to divide C cookies among P people? C plus P minus 1, choose P minus 1. How many ways are there to divide C minus 1 cookies? C minus 1 plus P minus 1, choose P. So the answer is going to be the sum, k goes from 0 to n, of C minus k plus P minus 1, choose P minus 1. Question?
Yeah.
Oh, not n, sorry, to C.
Couldn't you just add like a p plus 1?
Okay, yeah, so yes, we'll get to that in just 1 second. And then I'll ask you, then you can answer that. So I want to make sure everybody understands that this is a solution, but a painful one. We have to now evaluate this binomial sum. We've broken it into a bunch of disjoint events. This is going back to partitions. Let's look at the case where we have C cookies divided, C minus 1 cookies divided, C minus 2 cookies divided, C minus 3 cookies divided. How many ways are there to divide C minus 2 cookies? It's C minus 2 plus P minus 1, choose P minus 1. I add in an extra P minus 1 cookies. Cookie Monster comes in, gobbles up P minus 1 of them, that put in P minus 1 partitions, that partitions it into P people. Okay? Binomial sums are in general hard to do. What makes this one particularly annoying is both upstairs and downstairs are varying. There is a simple, elegant way to attack this.
If you add a P plus 1 person.
Right, so we've got the grad students, we'll add one other person, we'll call this person the professor. Okay? And the professor, out of the goodness of his heart, will take all the remaining cookies home to his kids. Okay, isn't that so nice of the professor? What happens now? If we have C minus 2 cookies that we're dividing among P people, the professor brings home 2. If we have 5 cookies that we're dividing among P people, the professor brings home C minus 5. It is the same as assuming we have P plus 1 people. So add a person who gets remainder. This is the power of having the right perspective. If you look at the problem the right way, the calculation becomes trivial. If you look at it the wrong way, it is extremely painful, and it will be very difficult to get it to work out. But by adding one extra person who takes the slack, we now have this sum. So not only have we done probability problems today, we've actually proven some really big theorems in binomials. We have ways to evaluate sums like this. It all comes down to, can you tell a good story? That is the hardest part about all of these, is figuring out how to tell a good story. The more of these problems you do, the more experience you have, the easier it becomes. Okay? How many of you have ever played the lottery? Don't. Okay? Lottery is for the most part a bad idea. It raises tax money, which is good, but it's essentially a tax on people who cannot do mathematics. If you're playing small amounts, that's fine, and you can afford it for fun, sure. Do not spend significant fractions of your money on the lottery. Let's talk about probabilities of winning. Okay? Anybody want to tell me a common lottery system? I'm actually happy that people are not rushing out and saying, oh yes, when I... So maybe they're numbered 1 to 36 and choose 6 numbers. What are the 2 different ways we could do this? Yes?
Exclude 30 numbers.
We could do exclude 30, but what do I mean when I say we choose 6 out of 36? So either ordered or non-ordered, that's one way. Normally we don't care about order. What else could we do? With or without replacement. Which do you think is easier to win, with or without replacement? Without replacement, because then you know I don't have to worry about how many times is a particular number taken. So let's do without replacement. So what's the probability that you win? You get all 6 numbers right. What should that probability equal? And what's the number of ways you can choose 6 numbers? 36 choose 6. So you can use this to figure out, is it worth playing this game? You know, what is the probability of winning? What if you do it with replacement? Is this easier or harder? Much harder. Now you get to do all these wonderful cases. I have one number 3 times, one number twice, one number once. I have 2 numbers 3 times. I have 3 numbers twice. You can go through all those different cases. What's the most dangerous thing when you go through all these cases? Double counting. What else? Missing something. You do not want to do this. Whenever you start having this massive tree of all these different things to count, it is a recipe for disaster. Almost surely you will make a mistake. What's the best way to calculate the probability? Best way, how should we calculate the probability? Nope. Best way to calculate the probability? Simulate. Right? Can you start to simulate? Is there a way to try to simulate this and start to look at how many different ways? Do you think that there might be a formula? Do you think there might be a nice formula? If I replace 36 with n and 6 with k, I have to choose k numbers from n. There's a really nice formula. The total number of ways is a polynomial in n, and the degree is going to depend on k. Maybe there's something similar, and I can try to guess the pattern by doing a brute force enumeration. So you can definitely try something like that. What problem do you think would be very useful in solving this? What problem is probably useful? We can go home if somebody says it. The cookie problem. It turns out the method of the cookie problem of putting in the partitions is exactly what you need to count something like this. It goes through in the book, it talks about choosing spaces between numbers. So I'll let you read that. If people want to talk about that more, you can see how the probability changes. All right. Have a great weekend. Enjoy the kickoff.